Hi there, this is Mr. Zand again, and I am going to talk to you about Unit 6, which is momentum. Now, before we get started, I'm going to just show you some slides. Here is a slide. You can see it right now. Here is a looks like a steering wheel, and then they've got this little bag coming out of the steering wheel. It looks like an airbag, and it is an airbag. All right, that's the first thing I want to show you. What else? Oh, these are great. I don't know if you've ever gotten a chance to jump in one of these things, but they're amazing. You can do flips, you can do whatever. You can land directly on top of your head in these giant foam pits, and it doesn't hurt. It feels amazing. They're lots of fun. Here's another photo. Here's a photo of a person jumping out of a building and then getting caught in this giant. I guess you would call this like a fire trampoline, maybe. The fire department used to use these to catch people jumping out of the buildings, and it would not kill them. Marshmallows. Let's look inside this. What is this? This is an American football helmet and a bike helmet. Notice this stuff. It's a cross section of it. It's very, very thick there, and well, it's not as thick as a bike helmet is actually. Interesting. Foam pads on the side of a gym wall. Again, football pads and knee pads here. You got knee pads here. Oh, look at this little dog. So cute and fluffy. And a even fluffier bunny. So, why do you think I'm showing you all of these images? What do they all have in common? Well, once you understand what they have in common, you might even start to revise what you usually think of as being soft or being safe. All of these things, what they do is they take a force and they slow that force down, but they slow it down over a large distance, a larger distance than would normally be had. For instance, let's take a look at the foam is the easiest way to think of it. If you were going to jump off onto the ground, you would, let's just say like you fall and you just jump and you land right on your backside, on your butt. You land on your butt, it's going to hurt, I think. But if you land on your butt inside of a foam pit, it will not hurt. And that's kind of weird. Why is it true that it won't hurt if you jump on your butt in a foam pit? I mean, think about the physical reasons why that happens. It's because you slow down over a greater period of time. You've got the same force coming down. You could be dropped from the same height. And it would hurt if you hit the floor. But it would not hurt if you jumped into a foam pit like this. Imagine the boy jumping right here off of this little side railing that he's on, and he jumps directly onto the floor, the same floor that's shared with the foam pit. But the foam pit is filled with foam. The foam slows him down over a longer period of time than the air does right before he hits the ground on the side over here. So the force is the same from the boy. He's dropped with the same amount of force. And the gravity accelerates him the same amount, but he slows down over a longer period of time with the foam. So this could be a new definition of softness. So if something is soft, it just slows down a force over a greater period of time. Like this. This slows down the force of this person falling, and he would have hit the pavement and died because it'd be such a sudden change in force over a small amount of time, but now it's not. Same thing with marshmallows. Marshmallows are really squishy. Means if you put a force to it, it takes a long time for it to stop. Same thing with these. These are what helps protect your brain from sloshing around too much inside of your skull. It reduces a force that's on your head over a longer period of time. Same thing with this. these little side mats, these safety mats they put inside of gyms, they do that for this reason, to slow down the force so it doesn't hurt. Same thing with the pads. And with a dog like this, if it was a hairless dog, first you'd be grossed out, but you'd also be thinking it's not as soft as this little sucker right here. This little guy, look at him. He's just a little puffball with eyes and a little nose. Oh, this little guy, it takes a long time for a force of, let's say, your hand, which is it's a very small, soft force, a very low amount of force, but it takes a long time for it to slow down until it eventually reaches the skin of this little dog. And the same thing with this bunny. It's a new definition of softness here. It just takes a long time to slow something down. That's what soft is. So, I'm going to write a little formula here. And I've been talking about it so far. I've been talking about force. I've been talking about time. So force times delta t. Force times the change in time. This is the change in time. Change in time. Equals impulse. We'll call it an impulse now. So if you have some object, let's just say it's a ball, and it goes and it hits something else. Let's say this is a brick. A ball hits a brick. The force that this ball impacts on the brick and the amount of time it's in contact with that brick is its impulse. If it's a longer amount of time that's in contact with that brick, it'd have to be, if this was larger right here, and it's the same amount of force, it would have to be a larger impulse. Does that make sense? Let me think about that. Change in time. So it would be the time in which it is in contact with this and the amount of force it's in contact with this. And the force would be the same, but the change in time would be greater. So the impulse would be greater. Okay. I guess we have to accept that. Unless I think of it. It sounds a little counterintuitive when I say it that way. You've got a greater impulse if the amount of time is greater. Of course, it makes sense if there's a greater amount of force, it's a greater impulse over the same amount of time. I think that makes sense. Okay. Anyway, that's impulse. And now I'm going to tell you something that is just going to be weird, and I'm okay with it being weird. It is something called momentum. And you've probably heard of that before. Momentum, I'll put the word here. Momentum is mass times velocity. And velocity is a vector. So momentum is a vector. Force here is a vector, so impulse is a vector as well. Impulse and momentum. Momentum is often thought of as the best way I can describe it really is like the oomph of something. So if something has greater oomph, the more momentum it has. So it has, let's say that you have a ball, again, let's just use a ball, and it has a higher velocity than another ball is identical to it. So this is a smaller velocity than this. So that means that this ball up here must have greater momentum. You can also have a larger mass, and perhaps this has the same momentum as this guy up here. So this momentum could be the same as this. A larger mass, but with a smaller velocity. That's momentum. It's the oomph of something. So how do we get to this? Well, I'm going to show you something pretty cool here. We're going to start off with our dear friend F equals ma. Praise Newton. There we go. Let's get our F equals ma. Praise Newton right here. F equals ma. Right. So F equals m times delta v over delta t, right? That's what acceleration is. The change in velocity over the change in time. Okay. Well, I'm just going to rearrange this a little bit. We say force times delta t equals m times delta v. All right, this sounds okay. So force times delta t. And remember what delta v is. It's actually the final velocity minus the initial oh shoot, the initial velocity. There it is. Ignore this little dot. Okay. All right, that sounds good. So we've got the force times delta t equals mvf minus mu. This is great. So now we can see that an impulse equals the change in momentum. Because this right here, mv, is actually the same thing as momentum. Ah, I didn't give you the number or the letter for momentum. Momentum's abbreviation, I'll use this color, momentum's abbreviation is P. P. We use P for momentum. And the units for momentum are kilograms times meters over seconds. Same thing for impulse. Kilograms, meters per second. There's no special unit for that. It's just momentum. Kilograms times meters over seconds. So in this case over here, we can now substitute. This is the final momentum. Call that PF minus PI. So that's a change, which also equals the change in momentum. So if you take a look at the impulse, impulse equals the change in momentum, and impulse equals the change in momentum. That should make sense. So if you have an object going with lots of momentum and then going to no momentum, that change is an impulse. It's a force over a period of time. Okay, so all I did is I just told you a whole bunch of random things and then related them to each other, kind of, with this formula right here. So let's do a couple problems to get some intuition about this. All right, let's do that.